Okay, so the next speaker is Sulagna Bhattacharya, and she will talk about gravitational waves as a probe of our particle dark matter.
Yeah, so this talk is going to be a bit different from what we have heard since morning. Thanks to Deep and Raghu, who has already introduced some part of the, some introductory things about the work. I'd like to thank the organizers for giving me this opportunity. So let's start. So dark matter needs no introduction. It has its evidences at all scales, from galactic scale to CMB, gigaparsec scale. As you can see, its viable candidates ranges over like 70 orders of magnitude. So I'll be talking about GeV particles, like heavy dark matter particles. And the Raghu talked about this gravitational production of dark matter particles, and it's having no interaction with the standard model. But as we don't know about dark matter, let's check the other story. What if it has some sort of interaction with the standard model particles? So if it has some sort of interaction with the standard model particles, then the three popular probes are considered as direct detection, indirect detection, and collider search. So in direct detection, we expect that the dark matter particle will hit a standard model particle, and from the recoil we will detect the dark matter. And in indirect detection, the dark matter particle can find its antiparticle and then annihilate to standard model particles. And collider search, we think of missing energy channels and try to search for dark matter particles. In this talk, I'll be concentrating in non-annihilating heavy dark matter particles, and I will tell you why we need non-annihilating and heavy dark matter particles. So the x-axis in this plot is the dark matter particle mass, and the y-axis is its interaction cross-section with the nucleon. And these regions above the lines are ruled out because we have not yet detected dark matter. So these are all terrestrial experiments spanning like in US, in Italy and all. So so as you can see, like in the GeV 1 to 10 GeV, we are quite good with the experiment, but it has some problems. So if we go to the high cross-section part, then the dark matter particles may interact before even reaching the detector. And if we come to the smaller cross section, then whether a neutrino is hitting our detector or a dark matter particle is hitting our detector is a bit confusing, and we cannot we need very higher statistics to say whether a neutrino or a dark matter particle is hitting our detector. And as we go till to the heavier dark matter mass, we need more and more. We lose in the flux, being dark matter density constant. We lose in the flux, and it will take a long time to get detected. Now, if we look at the celestial detectors, the sun, earth, neutron stars and stuffs, then we are like 33, 36 orders of magnitude better to probe dark matter. So if we talk about the smaller cross-section regime, then we need neutron stars, something whose escape velocity is very high, so that the dark matter particles, although being very small, like very loose, weakly interacting with the standard model particle, can get captured if we try to probe them with neutron stars. But sun and earth or any stellar objects can do better in the higher cross-section regime. So I will talk about another probe that we can explore using gravitational wave detectors. So dark matter capture. Deep has already introduced about it on 31st evening. So basically there are galactic dark matter particles and there are celestial bodies. So these galactic dark matter particles, if having some non-zero interaction with the standard model particles, may interact, and within their trajectory they may lose the energy such that its final velocity is smaller than the escape velocity of that celestial body. And if it is so, then it will be trapped inside the celestial body. And this is how you capture the dark matter particles. So a little bit of formula. So it will hugely depend on the dark matter density, ambient dark matter density, and its velocity distribution. And this NN is the stellar targets. So more massive your celestial body, more number of targets. And G1U is the probability of getting captured just after a single collision. It has to do with the cross section with which the dark matter particle interacts with the standard model particles. If it's very weakly interacting, we'll have to come up with the parameter space in which just after the single collision it gets captured. So just to give you a sense, if you take a 10 to the power 5 GeV dark matter particle with an interaction of 10 to the power minus 45 centimeter square, just to give you a number, the proton-proton cross section is 10 to the power minus 26. So it's 20 orders of magnitude less cross section, and with the temperature of the neutron star being this and the mass, so the total captured dark matter mass within its lifetime will be about 10 to the power minus 15 solar mass. So a neutron star with 10 to the power 10 years of age can capture 10 to the power minus 15 solar mass of dark matter particles within its core. So now when the dark matter particles are captured, depending on its mass, it will interact in the celestial, in the body more and more, and it will lose energy, and it will thermalize inside the object. So depending on its mass, it will thermalize towards the core. So heavier the dark matter particle, it will come towards the core and it will thermalize. So if you take the same numbers, like 10 to the power 5 GeV dark matter particle and the core temperature of the star being the same, then it will concentrate within the 5 centimeter of the radius, thermalization radius. So it's a very dense core it is going to form. So throughout its lifetime, it will capture enormous number of dark matter particles, and as they are coming towards the core and creating over density, it will after some time eventually collapse and give you a micro black hole. Why I will call it micro? Because the size of the black hole is going to be very small. So it depends on the collapse criteria. Like whenever n chi BH gives you the number of the dark matter particle that can be captured throughout the lifetime of the celestial body. So whenever it starts self-gravitating or Chandrasekhar collapse, depending on the nature of the particle, if it's a boson, it will go self-gravitating condition, and if it's a fermion, it has to obey the Chandrasekhar criteria. Depending on the nature of the particle, it will collapse and give you a black hole inside the core of the celestial body. So just to give you the number, if you put 1 GeV as neutron star mass and put it in n chi Chandrasekhar, you can retrieve 10 to the power 57 GeV, which is like 1 solar mass, 1.4 solar mass, the limit of Chandrasekhar collapse. So as we are talking about this heavy dark matter particles, they will eventually form minuscule black holes of mass like 10 to the power minus 15 solar mass, and to create that micro black hole inside the neutron star, it will take the time around 10 to the power 8 years for the numbers I have given. So now we already have a small black hole in the core of the neutron star, or I'm talking about neutron star, you can do it in any celestial bodies, that the parameter space will be changed. So now we already have a small black hole inside the neutron star. So then that black hole, depending on its mass, will eat up the neutron star or Hawking evaporator. So if that black hole being in a sweet spot such that the black hole can eat up the whole material of the neutron star, then we will see if the black hole has 10 to the power minus 16 solar mass of mass, then it will take around 10 to the power 4 years to eat up the whole neutron star. So in some particular parameter space, we can have the collapse time. So the time of forming that small black hole plus that small black hole eating up the whole material of the star within the edge of our universe. If this happens, then we should see some low mass black holes. So if we start with a binary neutron star system that can capture enough number of dark matter particles, and it can get transmuted to a similar mass black hole, And we should see the similar black hole mergers in the LVK data, as we can see the binary neutron star mergers. But non-detection of this low mass black hole can set stringent constraints on the dark matter parameter space. So these black holes that we talk about, these low mass black holes transmuted from a celestial bodies, are called transmuted. So LVK recently searched for low mass black holes, and they concluded that they have not seen any low mass black holes. So anything that they see in between 1 to 2.5 solar mass, they label it as a neutron star merger without even seeing its electromagnetic counterpart, because so far we have seen the electromagnetic counterpart for only GW170817. So as LIGO says that, as LVK says that they have not detected any such low mass black holes. So from the non-detection, we can put some upper limit on the merger rate of these kind of black holes, low mass black holes. So the x-axis is the charge mass, and the y-axis gives the merger rate of the low mass black holes. So if the number of events is greater than, as you can see any low mass black hole merger, so any events greater than 2.303 is excluded in 90% confidence limit. And we will need this VT. VT is just, this is merger rate per gigaparsec cube per year. To get the number of events, you need the volume and the time of the detector. So this is basically the detector sensitivity. Now, how do we calculate the theoretical merger rates of these binary black holes? So these will be hugely dependent on the merger rate of the binary neutron stars, as we will start from the binary neutron star system, and it will then capture dark matter particles and then give you the transmuted black holes depending on the dark matter mass and its cross section. So this will be more discussed. Soon by Ranjan, I guess. So my main point is to tell that it will hugely depend on the binary neutron star merger rate. And where does the dark matter parameters comes here? Because if we have to see them in the LIGO data, we need them to be transmuted within the age of our universe. So T0 being the age of our universe, and TF is the time of the formation of the binary, and tau trans means the total transmutation time, that it from neutron star it will go to the black hole. These all things should be smaller than the age of the universe. Then only we can say that, okay, we should have seen these all things in the LIGO data, but we cannot see this, hence we can constrain the parameter space. So all the dark matter parameters for which this merger rate times the sensitivity of the detector gives you events more than 2.303 are excluded. So here comes the first result. So with the current LIGO data that we have and the merger rates that we have, it is very, it has a lot of uncertainties within it. Like the merger rate given by LVK collaboration for binary neutron stars is now 10 to 1700 gigaparsec per gigaparsec cube per year. So this is a very uncertain band. So we have done some statistical analysis, and the red region that we see is the current exclusion limit that we get from LVK observations. But you may now say that what is that PSR thing? So if this whole story works, then looking at an isolated neutron star can give you some excluded parameter space. Because if you are looking in a neutron star, and as you are seeing that it is still there, will exclude some dark matter mass and the parameter space. And as you can see, it is doing more better than the LVK data that we have right now. But the thing is, single neutron star will be we can beat these single neutron star constraints with higher statistics of the gravitational wave events, and that is shown by the forecast bound. Like where we take that when the sensitivity of the detector is more than is 50 times the sensitivity that we have now, then it can exclude a huge bunch of parameter space, where this LZ2022 is the direct detectional bound from the terrestrial experiments. So they lose their sensitivity in this high dark matter mass. So gravitational wave thing can do better if there are still non-detection of low mass black holes. And as Deep talked about, these bosonic particles can form the BEC states and all. These calculations you can do for fermionic case and BEC case also. But our point is to see whether there are low mass black holes or not. So now, The main question is, as I was discussing, so whenever LIGO sees an event of 1 to 2.5 solar mass, it labels it as a neutron star. But we can tell you that there can be 1 to 2.5 solar mass primordial black holes. There can be 1 to 2.5 solar mass, this kind of transmuted black hole. So how to distinguish whether we are seeing a binary neutron star merger or a binary black hole merger? So it turns out there are some exploration has been done. One of them is looking at the tidal deformability. So tidal, for black hole system, it has to be 0. And NSBH and NSNS system will give you some non-zero values of the tidal deformability. But what we are trying to see is whether we can do something with the waveform of these low mass black holes and binary neutron star merger. So these are all like theoretical stuffs, like how we get the strain, and you can write the strain in amplitude and phase. And the main part that I want to focus you on is the luminosity distance. And then the plot shows you the x-axis the frequency and the y-axis the strain. So delta L by L that we measure. So for this, I have taken a 1.35 solar mass binary black hole waveform, and for a 1.35 solar mass binary neutron star waveform. So why 1.35? So from the LIGO data, it has been seen that the binary neutron star merger distribution peaks at around 1.35 solar mass. So this red line that you see in the plot is for the binary black hole merger. But all the other blue shaded things are for the binary neutron star mergers. The problem with the binary neutron star merger waveform is it depends on a lot of microphysics because it has a matter effect. For black hole is just 2-point particles which are inspiraling with each other and then they are collapsing into one. But for binary neutron star, they will form a dumbbell-like shape and then they goes the further collapse due to the strange matter effect. So this equation of state 2H and this 2B are the two extreme cases, like the stiffest case and the softest case. So you can see, like in the inspiral part, all of the equation of states and the black hole are quite well. I mean, they match each other quite well. But in the post-merger part, they have like when the frequency is around 2000, 3000 or something, then they have a second peak for the neutron stars. So the softer the equation, the stiffer the equation of state, the peaks happens earlier. So for 2H, it is around 2000 hertz. And then we go to this BH, lambda phi, then this SLI, and for the EOS2B, which is the softest equation of states, that is also this line, which more or less mimics the black hole. Because that is the softest equation of states, and in this, I mean, softest means given the same mass, it has the smallest radius. So it is very much compact and behaves like a black hole. So what the inspiral? Yeah. So I have not plotted like for the inspiral phase. So I have started plotting from the post merger only, just to show the difference. Yeah. So like this is a smaller than, I mean, not starting from 0. The scaling is not starting. So after inspiral, it falls as like f to the power minus 7/6 for like perturbative calculations for black holes. Yeah. So what we can do is that we can calculate some factor called fitting factor. So how does a BBH waveform can fit the BNS waveform? So the noise weighted inner product is defined by this, where Sn is the detector PSD unit, power spectral density. So we have the BBH 1.35 solar mass BBH waveform, and we have the 1.35 solar mass BNS waveform. If the fitting factor is 0, then it doesn't fit the model at all. If it's 1, then it fits perfectly. So in the inspiral phase, what we see, like if our signal is a BBH, if we have a BBH waveform, and we are using this equation of states, Then in the in-spiral, we see the fitting factor is quite good, like 0.97, 0.98. And as we go from the stiffest to the softest equation of states, like in this direction, the compactness of the neutron star is getting more, then we are seeing that the fitting with the black hole waveform is better. So with the 2B equation of states is more or less 1. But if we look at the post-merger thing, so the in-spiral phase is done from 0 Hertz to 1500 Hertz, and the in-spiral is done from 1500 to 4000 Hertz. Because after 4000, the detector PSD is so high, it doesn't depend if you are integrating from 4000 to 10,000. So if you look at the post-merger part, you will see that for the stiffest equation of state, like where the compactness is not that high, it mismatches with the binary black hole data a lot. Whereas if you go to the most compact equation of states of neutron stars, you will see that it matches the data more or less equally. So if a neutron star with 2B equation of states merging, then it is quite impossible to distinguish whether you have seen a low mass black hole merger or you have seen a binary neutron star merger. But any questions? Yeah, but later what you can calculate from this fitting factor is a Bayes factor, Bayesian evidence over if you see an event. So what is the probability that it is more BNS than BBH given the data? So that can be found from this formula. So you can calculate the fitting factor, and rho BNS is basically the SNR of the binary neutron star event. So what we see in this plot is the x-axis is just the luminosity distance, like how far the event is happening, and the y-axis is the Bayes factor, that given the event, what is the probability that it is a binary neutron star or a binary black hole. So as you can see, if you go to the low luminosity distance part, with the 2H equation of states is doing best. Like any Bayesian evidence which is greater than like 31 in Jeffrey scale, we call it a strongest evidence, but we take it as 100. So if you see, like for low luminosity distance, like if the merger is happening quite close to us, then any equation of state can be ruled out very easily by analyzing the waveform, except this 2B, because this 2B tend to behave just similar like a binary black hole, because given a same mass, its radius is very small that it acts as a point object. But if you forget about 2B, starting from SLI, like till 300 megaparsec, just by analyzing the waveform, you can clearly have Bayesian evidence for with them being binary neutron star. So we need to change the merger rate that we see. So there are some theoretical neutron star merger rate which comes from the star formation history and all. The left one, you may like, I am interested on the neutron star merger rate only. So it is as a function of redshift. So you can see that it peaks around 2.2 or something. That's basically from the Madhav-Dickinson star formation rate. So as it peaks there, so the merger rate also peaks there. But the main point is to see that this is the theoretical neutron star merger rate as a function of redshift. So now if this thing has to be true, that we given a 1.1 to 2.5 solar mass thing, if we cannot distinguish whether that is a low mass black hole or a neutron star, then this rate has to be changed, because at redshift 1, 2, it is totally indistinguishable whether that was a binary black hole or a neutron star. So what we see, if we plot it with the luminosity distance in megaparsec, first we take that there is no such low mass black hole. Everything that we see is a neutron star. So if this has to be the case, then till 400 megaparsec, I have done this calculation with the SLI equation of states only. Like SLI is this one, the peak around 3200. So with the SLI equation of state, I mean, you can do it better with the 2H equation of states just from the fact that it is the most steepest equation of state. So with the SLI equation of state, what we see that if we are within 400 megaparsec, that what we see as a binary neutron star merger, there will be binary neutron star merger if we just do the analysis with binary black hole model to it, because the detector is so sensitive in this luminosity distance, we can clearly distinguish. But what happens after 400 megaparsec is that we have to give some benefit of doubt, and we cannot say whether the compact object that has merged are binary black holes or neutron stars. So this is basically from where the binary low mass black hole, LMBH means low mass black hole merger rate starts coming in. It comes in the calculation just from the reconstruction that we have of the merger rate of the neutron star. So as we go far and far, you see it becomes like the merger rate of a neutron star and a merger rate of low mass black hole becomes equal, just from the fact that we cannot distinguish from the waveform that whether its origin was a neutron star or a low mass black hole. And in this case, as we are talking about low mass black hole, this low mass black hole doesn't have to be from the neutron star itself. It can be primordial black holes or something, or boson stars and things like some exotic black holes, not astrophysical. So with higher luminosity distance, their merger rates are like probability of them being a neutron star or a binary black hole is half and half, and this is the observed merger rate. This maroon line from here, this is basically the blue line in my plot, and I have cut it in the 5000 megaparsec luminosity distance because just to give you the number, this will be around redshift 0.07. So you are just seeing this part of the plot. So up to 400 megaparsec, BNS mergers can be identified with strong evidences, and with higher luminosity distance, it just becomes inconclusive that what we are seeing. So from Deep Stock, he was more specifically talking about, like, we can see if the states are bosonic or they are forming Bose-Einstein statistical Bose-Einstein condensate inside the neutron star, and with more data from the gravitational wave event and low mass black holes, you can shed light on it. But that is true. But the main problem is we still don't have the technology to distinguish beyond 400 megaparsec that whether two neutron stars are merging or two low mass black holes are merging. So it seems that with O5 upgradation that LIGO is going to have, it can look up to 250 megaparsec. And 250 megaparsec with its higher sensitivity, it can probably do better with distinguishing. Just if they fit a low mass black hole model to a binary neutron star model, they can just conclude whether they have seen the binary neutron star merger or not. And also there are experiments called NEMO, Neutron Star Extreme Matter Observatory, proposed by Australian people, which is more sensitive in the post-merger part. Post-merger means the higher frequency part after 1000 hertz. They will be more sensitive. So these kind of instruments can give you better Bayesian evidence, and also the Cosmic Explorers and Einstein telescope with their higher sensitivity. So the take home is gravitational wave can shed light into particle dark matter theory, and if there are no detection, then it can exclude things quite well. But if there are low mass black holes, then how to distinguish it? So given confirmed events like this 230529, 190418, and all these things where we have seen compact objects of like which can be heaviest neutron star and lowest black holes, cannot be astrophysical from stellar evolution theory, these kind of black holes can still work as a, like these kind of black holes can still give you hope that this kind of dark matter capture and then dark matter capture induced collapse can be a viable solution. And without an electromagnetic counterpart, it is very hard to conclude whether two neutron stars or two binary black holes have merged. And in distinguishing it, we need the full in spiral past plus post-merger part, because as I have showed you, that the post-merger part has the most most distinguishability between a binary black hole waveform and a binary neutron star waveform. So I want to thank my advisor, Basudev Dasgupta, and my collaborator is also sitting here, Ranjan. And for them, doing physics has become fun and easy. And these are some references regarding this talk. And thanks.
Okay, so now time for questions.
All right. So you presented the results about the distinguishability of the mergers, and is your benchmark reference point the SLI equation of state, or and how would the conclusion change in the worst case scenario, so for 2B?
Yeah, that is the case. I mean, 2B is anyway ruled out from the GW 170817 electromagnetic observations and observations of different neutron stars and their spins. 2B is not a very very acceptable equation of states. So if you go to 2B, then you cannot distinguish whether that is, I mean, that is more like a black hole. You see that with the lowest luminosity distance also, the Bayesian evidence is around just 10-20.
Okay, so we take just the equation state proposed by Duchamp and Hensel as the most conservative.
Okay, yeah. So if you go more and more towards the stiffer equation of states, you do better. Yeah.
So, as you have already pointed out that that's very much difficult in some regime to distinguish between neutron star merger and black hole mergers. So, but in one of
low mass black hole.
Yes,
yeah.
yes. So, in one of your slides, you are also mentioning about the tidal deformability. So can that break the degeneracy between these two events?
Yeah, of course it can make, but the tidal deformability things come in the calculation in the 5th post-Newtonian correction. So the tidal, the lambda, the capital lambda scales as m by r to the power 5. So in the 5th post-Newtonian correction only you can incorporate tidal deformability, and for that also you need events which are close by. So the main thing to look at is the closure events will give you good statistics, and the further event will not.
So are you saying that even I include this tidal deformability thing, then also we would have the degeneracy?
Then also we will have the degeneracy at a higher luminosity distance.
Okay.
Yeah.
Thanks.
Okay, so maybe, yeah, I have one question, one comment. So could you go back to the slide with exactly this one with the constraints? Maybe you said that, but I missed. So this missing pulsars thing, what does it?
So this missing pulsar thing is not an exclusion. It's just this hatched region talk you about the parameter space that can be responsible for missing pulsar. So in the galactic center, there are theories that there are some missing pulsars. We should see more pulsars there, but it can so happen in the galactic center as you have the dark matter density very high. So if your dark matter density is very high, then this rho chi will win. So it's like in galactic center, it's like any code profile will give you a very high dark matter density. And if it is so, then it will be very easier. Like for these neutron stars to get transmuted to a black hole, we need a very high lifetime of neutron star and a very high dark matter dense region. So in galactic center, we have dark matter density very high. And if these neutron stars can capture this kind of dark matters, and they have by now be a low mass black hole. So that is why probably we are not seeing the the pulsars. And this parameter space of bosonic dark matter can explain this missing pulsar region. Yeah. It is just to show that with higher statistics, if LIGO sensitivity is high, it can even with non-detection can rule out these scenarios. Yeah.
Yeah, and the comment is that a few months ago, maybe we'll go back to, no, exactly the plot, but this one.
Yeah.
Yeah, so that like a few months ago, LZ experiment published updated results,
Yeah.
which is like almost a factor of 10
Almost a
better.
factor.
So yeah, so maybe it does not cut out
Yeah,
much
because
of your...
like I mean, we lose with higher dark matter density, we just lose by 1 by m chi in the sensitivity. So yeah, I agree that it can go
just
to
some small
some
range.
this part, yeah. But yes, yeah, thanks.
Okay, I don't see further questions, so let's thank again.